So we finished last time by talking about a problem. We said, here's an outline of what we would do. Well, let's just do more than talk about the outline. Let's actually go ahead and finish the problem. So recall, what was it? We had 3 points, 271, 828, and 182. And we want to find the plane which contains those 3 points. And okay, so whenever you're looking for a plane, you say, I need 2 pieces of information. I need a point, and we picked a point, 271, and last time I put a vector notation. No, point notation, parentheses. But more importantly, we need the vector, the normal vector. And the way we can go about finding normal vectors in most cases is to say, well, I need to find something which is perpendicular to my plane. So one way to do it is to find 2 things which are in my plane and cross them. Because cross products are really good at making perpendicular things. So in particular, I said, well, suppose I look at my 3 points, and I say, okay, here they are, maybe. Well, look, we just need intuition. I form new vectors going between 2 points and a different vector going between 2 other points. And I say, look, these are vectors in the plane. And now, if you take their cross product, you'll get a new vector. Probably it would be pointing this direction if our picture were accurate. You cross V, which is perpendicular to U, and it's also perpendicular to V, which means that it's perpendicular to this plane that contains both U and V. Well, that's our plane. That's the plane we want. So, here we go. Well, let's make this our initial point, and these other 2, these terminal points here. So, going from 271 to 828. Well, 2 to 8, 6. 7 to 2, -5. 1 to 8, 7. Cross, 2 to 1, -1. 7 to 8, +1. 1 to 2, -1. Okay, so those are my 2 vectors. Okay, all right. Now, what do we do? Well, we're going to take their cross products, and I think there's a mistake here. Let me check. 2 to 1, down by 1. 7 to 8, up by 1. 1 to 2, up by 1. Yeah, that's a +1. All right, so taking their cross products, this is going to be I, J, K, 6, -5, 7, -1, 1, 1. So this would give us, well, -5i, then -7j, and +6k. So that's the downs. Now the ups, and remember the ups we're going to subtract. So if we went up, we'd have +5k, but we subtract, so -5k. Here we'd have +7i, but we subtract, -7i. Here it's +6j, but we subtract, -6j, which would give us -12i, -13j, plus k, or -12, -13, 1. Now you should always sort of double check. Dot products really quick. 12 -13 plus 1, 0. -72 plus something plus 7. Well, okay, let's be more realistic here. All right, so -72 plus 65. That gets us up to -7 plus 7, 0. Good. Okay, so the claim is this is our normal vector. So I have the normal vector, I have the point. To get them together, we say our plane will be -12 times x, so the -12 comes from here, -13 times y, and then +1 times z. So these are my coefficients here, coming from the normal vector, is equal to something. So we have to find the d, and this is where the point comes in. So we plug in d. We plug in the point to get d. So x equals 2, so it'll be -12 times 2 minus 13 times 7 plus 1 equals D. And that's minus 24 minus 91 plus 1, which is a number. Well, that's negative 90. And then if I take negative 24 and I subtract 90, negative 114. So our answer will be minus 12x minus 13y plus z equals negative 114. Now, how can we check? Well, the plane has to contain these points. Now, it should definitely contain 2, 7, 1 if we did our math right. Minus 24 minus 91 plus 1. Well, that's minus 114. Now, here's the real test. It should also contain these 2 points. So, quick double check here. We'll change colors to do that. So, minus 12 times 8, that's negative 96. And we'll have minus 13 times 2, which is minus 26, and then plus 8. So negative 96 minus 26 plus 8. Well, what will that be? Well, if I combine these two together, what will I have? I'll have minus 122 plus 8. And if I combine those, I'll get minus 114. Check. Works out. Good. Okay, what about 182? Well, okay, another check. So 1 times negative 12, negative 12. Negative 13 times 8, well, that's like 80 plus 24, that's 104, but I'm subtracting. And then plus 2. So negative 12 minus 104, minus 116, plus 2, minus 114. Check. Good. So we can be 100% confident now that this is the right answer, because it is a plane, because it's the right formula for a plane. Something x plus something y plus something z equals a number, and it contains all the points. Good. Done. Done. Oh, it's not so bad, other than a few numbers that are a little messy, but that's okay. We're not intimidated by messy numbers. Now there's a second problem. It says the following. Find the line of intersection of the following 2 planes. Now, there aren't 2 planes given here, so we'll just make 2 planes up. Hopefully, we won't make anything too crazy. 2x minus y plus 3z, whoops, z. That's a very strange way to write z. 3z. There we go. That's better. Equals 11. And then we'll also say that, let's see, x plus 2y plus z equals 6. All right, so there we go. There's 2 planes, and it says find the line of intersection. So what are we talking about? Well, the idea here is suppose you have 2 planes. So suppose this is my situation. So I have 2 planes. So here they are. There's slightly different colors. And if you look at these 2 planes, they intersect. So the question is, how do they intersect? Well, the way that they intersect is they intersect right down and they form a line. So in particular, if we look at it, the intersection is that line right there. So the question is, what's that line? So we need to figure out 2 things. We need to figure out what's a point and what's a vector. And so we'll talk about how to figure those out, and we'll go through it one by one. Well, let's think about a vector first. Now, if you're looking for a vector, generally we say, can we use a cross product? And so we need to introduce some vectors. So let's think about what are some natural vectors we have for this problem. Because we have planes, the natural thing to work with when you have a plane is the normal vector. In fact, you could even say that that's what you normally want to work with. So our normal vectors we have for free, reading off the coefficients, 2, -1, 3, and 1, 2, 1. Okay, so those are the normal vectors. Now, let's think about what's true about this line. Now, this line is contained in the first plane, which means that the direction of this line is inside of the plane. And anything in the plane has to be perpendicular. So the normal vector is going to be coming right off the plane. It's going to be perpendicular to this plane, form a right angle. So in particular, the normal vector is perpendicular to the direction of the line. And same thing with this other plane. The normal vector for this plane, which is different, again, because this line is in that plane as well, also perpendicular. Which means both of these vectors we want are perpendicular to the vector we're after. So, in other words, we have these two normal vectors. We don't even need to know they are normal vectors, but we do know that they're both perpendicular to what we want. And if we have two things perpendicular to what we want in 3D, the rule is cross them, you'll get what you want. Okay, so there we go. We have a plan. So now we cross these two together. So we're going to get I, J, K. 2, -1, 3, 1, 2, 1. Well, what does that equal? Minus I plus 3J plus 4K. So those are my going down. And I wrap around. Now go up. Remember, when you go up, subtract. So this would be normally minus K, but I subtract, plus K. Plus 6, but I'm subtracting. So minus 6, that's I. And then plus 2, but I'm subtracting. So really, minus 2, J. So we get -7. So that's the I, 1 and 5. Okay, well, we do what we always do because we want to make sure we get all the points. Check, dot product. Minus 14, minus 1, that's minus 15, plus 15, 0. Minus 7, plus 2, plus 5, 0. Now, are we guaranteed that we did the cross product correct? Well, not quite, but it doesn't matter. We all now are guaranteed that this is perpendicular to both of what we started with, so it definitely points in the right direction. So our vector for our line is -7, 1, 5, or some multiple thereof. Okay, so the vector is done. Normally the point is a freebie, but now it's not so clear because we say, well, what's the point? There are infinitely many points in the plane, and there's infinitely many points on that line of intersection. So you just have to find one. Okay, well, how can you find one? Well, usually the easiest thing is to say, well, look, you have two equations here and 3 unknowns. And this is a case where you have more unknowns than equations. So you say, okay, here's an idea. I'm just going to substitute or pick a value and see what happens and go from there. So for instance, let's suppose I say z equals 1, just temporarily. If I say z equals 1, what does this become? Well, 2x minus y plus 3 equals 11, so that means 2x minus y better be 8. And x plus 2y, well, plus 1 equals 6. Well, that means x plus 2y better be 5. And now we have two equations and two unknowns, and that's something we're a lot more comfortable handling. And so, for instance, what can we do? Multiply the first equation times 2 and then add. If I do that, I'll get 4x plus x, 5x, minus 2y plus 2y. And that, see, that's why I did that multiplied by 2, so that I get cancellation. Gone. Then I get 16 plus 5 is 21. So I can conclude x is 21/5. Now, that's not the only thing I could have done. I could have done the following. I could have said, well, look, 2x minus y equals 8, x plus 2y equals 5. I could have multiplied this equation by negative 2, and then add. Because if we did that, we'd have 2x, and then we'd have minus 2x. Gone. Cancel. So that's why we multiply by negative 2. Minus y, minus 4y, minus 5y. 8, and then minus 10. Well, that's negative 2. So you end up with y equals 2/5. So now you have an x, y, z. And if you have x, y, z, you have your point. So our point could be 21/5, 2/5, and 1. Now, is that the only point? No, there's infinitely many. But the point is that if you have too many variables, you can say, oh, I get to pick some for free. Should I have picked z equals 1? Probably. I could have picked something simpler. Maybe z equals 0 would have given us something simpler. Or maybe y equals 0. It's just hard to know. You pick something and you see what happens. All right. You have your point and you have your direction. Put it together. And so we finally have our line. I like to write it parametrically. X equals, y equals, z equals. Start with my point. 21/5, 2/5, 1. Now, that's my point. That's the first part. Then the vector. That's my coefficient of the t. Minus 7t plus t plus 5t. And there we go. There's our line. And again, this point, maybe there's a better one. I don't know. But it is one. And that's the important thing. That's the important thing. All right. Good. Well, let's go on to our next topic. What's our next topic? Well, our next topic is sort of preparing us for what we're going to be seeing in the near future, which is surfaces, and it's also helping us sort of start building up our intuition. So here, let's sort of say, what's our 2D setting? So in 2 dimensions, we learned about something called conic sections, and we'll talk about why do we call them conic in just a little while. And the conic sections, there's a couple of them. So there's the ellipse, the parabola, and the hyperbola. So the ellipse looks like x squared over a squared plus y squared over b squared equals 1. By varying a and b, you change the ellipse. You can make it more or less circular. Parabolas, y equals some constant x squared, and hyperbolas, x squared over a squared minus y squared over b squared equals 1, or y squared over b squared minus x squared over a squared equals 1. Now, of course, you would say, are these the only hyperbolas and parabolas and ellipses? And no, because you can do things such as translation, absolutely allowed. You can also do things such as sort of rotation. And but the point is that after you say, look, after you translate and rotate, all your conic sections look like one of these. So that's 2D. Where are we going for? Well, we're trying to talk about quadric surfaces. That's our 3D analog here. And the thing becomes, well, how do you understand a quadric surface or a three-dimensional object? So the way we're going to approach it is to think about cross-sections. So in particular here, I have this shape, and we'll talk about this shape in a little bit. But you can kind of see that it's almost like a parabola, but three-dimensional. And it's upside down. And so suppose I wanted to understand what was happening. Well, the way I can do it is to slice it. So when you slice an object, what we mean is we have this surface out in three-dimensional space, and we're fixing a value. Now we can slice in either the x, y, or z, but I will say most of the time when we talk about slicing, we're going to slice with respect to z. So we slice and we say, okay, what do we hit? So in this case, what we do is when we slice, we'll get a circle. And it's going to be very common, by the way, for the next 30 minutes. We're going to see lots of circles. And as we vary our place where we slice, in other words, we're varying this value for C, we can see that as we go down, the circles keep getting bigger. But they get bigger in a certain way. So, for example, here, the difference between these two circles is a little bit more substantial than the difference between those two circles. So somehow there's a slight change of behavior going on. And we're going to try to figure out what's happening and why it's happening, and you get some intuition. So again, if you don't understand something, look in a slice. In fact, that's going to be a big philosophy that we have in calculus, is say, what's happening in our slices. All right, so we're going to look at a lot of surfaces and see what we can do. So our goal is to just start with an equation and start saying, what do I see? What do I see? So here we go. We'll start with a fairly simple looking equation. Z squared is equal to x squared over a squared plus y squared over b squared, where a and b are some various constants. Now, if it simplifies things, you can think of a and b as being 1. So z squared is equal to x squared plus y squared. Now, one thing you can think of as doing this, if I vary z, so in other words, I say, well, let's look at what's happening. So the xy plane, that's z equals 0. What do I get? Well, on the xy plane, if I have x squared over a squared plus y squared over b squared equals 0, the only thing I can get is 0. So in the xy plane, I get just, in fact, a single point, the origin. So this is an origin story. Now, what happens? Well, as z increases, if we think of this like a radius, the radius increases, and it increases at a nice rate. So in particular, if I move up, what I'll see is I'll see a circle. If I move up more, I'll see a circle again. But the key here is to say, how are the circles going? Well, it turns out that they're going at a very steady pace. So in other words, they grow essentially linearly with height. But of course, not just down, also, sorry, not just up, also going down. And so, the surface, if I'm slicing with respect to z, what I see are circles, and so I get this shape. Now, I don't just have to slice with respect to z. Suppose for a second I say, look, let's set x equal to 0. So if I set x equal to 0, that means I get what? Z squared is equal to y squared over b squared. Okay, what is that? Well, that says that basically z is y, plus or minus. So that's what we're seeing here, is we're seeing these straight lines. Z is some multiple of y, plus minus. So that's one of the reasons why we say it grows linearly. Okay, well, does this have a name? And the answer is yes. In fact, it's one we've seen before. This is the cone. And there you go. Okay, so now we've done the cone. Quickly, let's step back and talk about conic sections, cones. This conic actually comes from the word cone. And what it means is that you're getting slices of the cone. So, how do you get things such as an ellipse? Well, you can get an ellipse by slicing either parallel to the xy plane, if you vary a or b, but also you can get an ellipse by slicing at an angle. And so if you look at what happens here, so I'm slicing in at an angle, it turns out that that shape you form, it's an ellipse. Okay, well, how do you get another shape? Well, suppose I don't want an ellipse. Suppose I wanted to get something, say I want to get a hyperbola. How do I do that? Well, now slice this way. So if you slice that way, what happens is you get a shape, two sides, like so. And if you look at those two sides, what they form is a hyperbola. Okay, so a hyperbola is slicing up and down. Well, That leaves one left. How do you get a parabola? Oh, okay, parabolas are good. The way you get a parabola is you actually slice parallel to the edge here. So I want to slice just parallel to the edge. See, a hyperbola hits both sides. I want to get something which will only hit one side, but I don't want it to close up, because if I close up I get an ellipse. So if I do that, what I'll get is something that does this, and it grows as I go down. And it turns out that's a parabola. So these are called the conic sections because you get all of them from slicing cones. All right, good. We'll come back to those pictures as we go on. All right, x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. So if we're trying to understand things, the natural place to start is to say, let's take a look at a slice. So we slice. So for instance, suppose I want to slice and hit the xy plane, z equals 0. Well, what you see is some ellipse in the xy plane. So all right, so I see an ellipse in the xy plane. Maybe this ellipse. Okay, so that's what I see in the xy plane. Now we say, well, what if I want to be in the yz plane? Okay, set x equals 0. If I'm in the yz plane, I again, turns out, I see an ellipse. So I'm going to see a different ellipse in the yz plane. Yeah. And now, let's go to our last one. Well, what's our last one? What haven't we done yet? We haven't talked yet about the xz plane. So you cover that up, and what do you see? Well, you see another ellipse. And so, I'm seeing an ellipse. So here, what I'm seeing is I'm seeing a shape which is composed entirely of ellipses. So, something like that. All right, well, what do we have? This, it turns out to have a nice name, and it's called an ellipsoid. So, you'll see this fairly commonly, where part of it is like, oh, it's the conic thing and the oid. So the oid is sort of like the three-dimensional thing. This, by the way, is a really terrible picture. But hopefully you're getting the idea. Think of it like M&Ms. Now what's happening is, as you vary A, B, and C, it's almost like what you're happening is starting with the sphere. So if A, B, C are all 1, you have a unit sphere. And now what happens if I vary A? If A increases, it's stretching it in the x direction. Whereas if I increase C, I'm stretching it in the z direction. And so I basically am fine-tuning, saying I just want the right kind of ellipse. Most of the time when we see this, we'll look at this and say, aha, it looks a lot like a sphere, because it does look a lot like a sphere. In fact, we should have seen it when we saw the x squared, y squared, z squared. It's like, oh, that sounds like a sphere. Okay, so that's an ellipsoid. All right, so next one. So here, kind of similar, but also kind of different. X squared over a squared plus y squared over b squared plus, minus z squared over c squared equals 1. Okay, so different because of the minus. Now, one thing that might help us to figure this out is to actually rewrite it. So we can think of it as x squared over a squared plus y squared over b squared is equal to 1 plus z squared over c squared. So in other words, I'm moving the z squared over c squared to the other side. And now if I think about varying z. So for instance, in the xy plane, z equals 0, I get an ellipse. So I have an ellipse down here in the xy plane. And now as I move up and down, what do I see? Well, as I'm moving up and down, I'm increasing this z squared. It gets larger the farther away I move. And it doesn't matter whether I move up or I move down because of the square. So if I move up, I'm going to see even a bigger term. And if I move up again, I'm going to see an even bigger term. And similarly, if I move down, and if I move down. Okay, so my slices, when I slice parallel to the xy plane, so in other words, z equals to some constant, look like ellipses. But there are other slices I can take. Suppose I say, well, look, what does it look like in the yz plane? So I cover that up. And what do I have? Y squared over b squared minus z squared over c squared equals 1. Well, have we seen anything like that before? And probably yes, because it looks a lot like that kind of an expression, or this kind of an expression, where we have a difference of squares. So it means that when I slice, I'm seeing a hyperbola. So what's happening here is that I'm seeing a hyperbola coming through. And of course, that's if I slice in the yz plane. If I look in the xz plane, I'm similarly going to get another hyperbola coming through. So what I end up forming is this shape, which looks vaguely what you might call an hourglass, where it's going to get, it's a little thin at the middle, but then it gets bigger as you move in either direction. What does it look like? Well, the cross sections, if you slice up and down, look like hyperbolas. So they call this a hyperboloid. This is called a hyperboloid. Okay, well, let's look at something else. Minus x squared over a squared minus y squared over b squared plus z squared over c squared equals 1. Now what's the big difference here? The big difference is, over on this side, only one of the terms is negative. Over on this side, two terms are negative. Well, maybe that means it's twice as interesting. It's possible. Maybe. Well, let's find out. Again, we can do the same thing to start, which is, let's get x squared over a squared plus y squared over b squared. Well, what would that be? Well, it would be the following. I would have moved these terms across, so I'm going to move the 1 across. So I get z squared over c squared minus 1. So notice here it was plus 1. Here it's minus 1. Well, how big a change can that make to the shape? Well, a lot. Notice in particular, suppose I set z equals 0. If I cover that up, x squared over a squared, y squared, b squared equals negative 1. Not possible. You can't have things being squared and then add it up and get a negative value. You have to end up with something which is at least 0. But almost always it's going to be positive, which means that the slice in the xy plane is empty. It misses it. In fact, it's going to be empty up until you get up to z equals c. Why? At c, you're going to get to 0. So you're going to hit a point. And similarly, for negative c, you're going to hit a point. So it's missing everything between there. Okay, but then what happens? Well, as we move up from there, what we're going to see is now we're going to get positive values. And so we're going to get x squared and y squared equals some number, which means we're going to start seeing circles as we go up. So we're going to start seeing circles of some short shape. Okay, so we're seeing circles. Now, can we be any more precise? Say, how are the circles opening up? Are they sort of zoop, or are they more of a or are they something else? Well, to think about it, let's slice again. Well, yz or xz, but yz is very convenient for us to draw. So yz, cover up that first term. What do you see? You see something familiar. It's a hyperbola. But now the signs have been switched, so the roles reverse. So here, where the hyperbola opened this way, now the hyperbola is opening this way. All right. So you saw that. So for example, when we talked about hyperbolas before, there were sort of two ways for the hyperbola to open. So that's the difference. So what you were forming here is we're forming something that has sort of almost like two bowls. So a top bowl and a bottom one. And they follow a particular shape. All right, well, we're going to call this, because the main cross section that we see is a hyperbola, we'll call it a hyperboloid. And now we're going to say, whoa, wait a second, we have two things called hyperboloid which are very different. These things are fundamentally different. The properties of this one are not the same as the properties of that one. So we're going to give it a more refined name. So instead of just being a hyperboloid, we're going to say this is a hyperboloid of one sheet, which is to say it's just one piece. It's all connected. Whereas we're going to say this one is a hyperboloid of two sheets. So in other words, it's going to end up with two pieces. So there's two parts. It's disconnected. And the way you form them, one way to think about it, is if you go back to the hyperbolas here, it turns out that if you were to spin these, so for example, if you spun this one around, you'd end up getting a hyperboloid of one sheet, whereas if you spun this one around, you'd end up getting a hyperboloid of two sheets. So, all right. So the name hyperboloid, that's a fairly reasonable name to come up with. Okay, well, we're making great progress, and a few more to go. Rounding the corner here. So we're going to switch to something a little bit more simplistic. Here we are. Now we're going to have some things which aren't squared. So z equals x squared over a squared plus y squared over b squared. And in fact, we can kind of see what's going to happen. Because if we cover this up, in other words, we look in the xz plane, so we're slicing in the xz plane, we see, aha, this is a parabola. So it's a parabola and it's positive, so I'm opening up. So I'm parabola opening up in the xz plane. But if I cover up the x, z equals y squared over b squared, which means I'm a parabola, but I'm in the yz plane, and so I'm opening this way. So again, these pictures can be a little bit confusing, but the blue is slicing where I'm hitting y equals 0. The yellow is x equals 0. And I see the shapes I'm forming here are parabolas, and so you can sort of see where we're going. This is going to be called a paraboloid. Okay, so we're making paraboloids. Now, what happens if I move up? Well, notice I have something that looks like a circle. If z were negative, there's nothing. So it's nothing, nothing, nothing. Hit the xy plane, get a point at the origin, and then as we move up, we're forming circles. So what we're seeing here is we're seeing something that looks like this. And in general, the way we draw these are we have an a bowl. This is an upside bowl, not an upside down. So these are sometimes affectionately called bowls. And these types of surfaces are going to be important as we go on and talk about things such as classifying critical points. Because notice that a bowl has a minimum. So we're going to see this type of surface again. If you look at that surface, you might say, hey, if I turned that surface upside down and stretched it out, it looks a lot like the example surface that we had, and that is a very good observation. This turns out this is a paraboloid. So this is a paraboloid which has been turned upside down. So it's an upside down shifted paraboloid. So that's another example of that shape. All right. Well, what else do we have? Z equals negative x squared over a squared plus y squared over b squared. And now, what is this? Well, if I cover this up, it's still a parabola, but the negative has an effect. The effect of the negative says that what I'm going to have here is I'm going to have in the xz plane, I'm going to have a parabola that goes down. So I have a downward facing parabola. However, in the yz plane, so in other words, I covered the x up, so that's the different slice, I'm going to see a parabola that's going to open up. And you have to remember that these are actually at 45-degree angles to each other. And now we sort of say, well, how does this work? Well, one of the things you can do is you can say, I don't just have to set x or equals 0, y equals to 0. I can vary them. So if you just think about what happens, suppose for a minute, we have the place where we chose x equals to 0. So suppose I varied x. Well, what would end up happening if I varied x, so if I said x equals 1, I'd have a parabola opening up and I shift down. So I'm going to have something doing this. So in other words, as I move along, I'm going to move down. On the other hand, if I had pulled out my other color, what would I see? So if I had blue and I varied y, what I would see is I'd start seeing a parabola that's moving up. And so that's okay. All right. Well, maybe, let's see. What else can we try to do to help us understand? Well, let's look at if I now slice with respect to z. Well, at z equals 0, I basically get more or less that says x equals y. But if I say z equals 1, what do you see? 1 equals negative x squared over a squared plus y squared over b squared is what? Well, it's a hyperbola. So if I move up and I set z equal to 1, what I'm going to get is a hyperbola. So I'm going to form a hyperbola shape. And similarly, if I move down, well, what will I see? The answer is I'll see a hyperbola there. So downstairs, I'll see a hyperbola. So again, lots of cross-sections are parabolas, and this is becoming somewhat of a Jackson Pollock work of art here. So let's try to understand it a little bit better. Let me try to do a better picture here. So I'm going to do my best impression to sort of see what's going on. So we're going to draw this basic shape here and talk about it. So here we go. This is what's happening. So in one direction, you see a nice parabola going up, and in the other direction, we see a parabola going down. And if you take a cross section, so for example, here's a cross section, you see a hyperbola. Now, this is a paraboloid, and we want to distinguish these two, so we actually give these names. So for this kind of paraboloid, we'll call this an elliptic paraboloid because the cross sections are ellipses. For this one, we're going to call it a hyperbolic paraboloid, but we almost never use that term in class. So for example, we'll rarely say an elliptic paraboloid, we'll say a bowl. And for this one, we're not going to say hyperbolic paraboloid, we're going to say saddle. So, why the word saddle? Well, because if you've ever seen a horse, you'll see that a horse, when you ride a horse, there's something that you put on a horse to help you ride it, which is a saddle. And so you can imagine that there's a horse here. And, well, you have to have a really good imagination. But imagine, of course, that this is a horse. Well, there's this saddle here. The saddle that you see on the horse, there's one direction, it's a parabola, but opening up. And in the other direction, it's a parabola opening down, which is good, because otherwise it would be very, very awkward to get on this horse. There we go. All right, horse. So, saddle. So, saddles are going to be actually very important. So both saddles and bowls are going to play a very nice role in what we talk about in the middle part of the course. So we're going to see both of them again. All right, we're almost done. So how do we finish up? We're going to talk about the following, which will actually be a shape we've seen before. X squared over a squared plus y squared over b squared equals 1. Now, you look at this and say, wait a second, you've drawn the wrong space. because you've put a three-dimensional set of axes here, implying it's a three-dimensional thing. But clearly, it's only two-dimensional because there's only x and y. There's no z. And in fact, z is missing. Missing z. Well, what does that mean? Well, okay, so it turns out that you could say, in fact, you could draw this in the xy plane, and you get a nice ellipse. But now, you say, well, but look, that's if z equals 0. What happens if z equals 2? The answer is, well, you get the same shape. Because when I'm missing z, that means that there's no z dependence. You have to imagine that I was consistent in drawing so that these were actually exactly the same. Similarly, if I shifted down, I would get the same shape. So what's going to happen is I'm going to get the same shape all the way up and down. And so we call this particular shape a cylinder. So it's almost like a straw shape. So we're cylinder going up and down. Of course, it doesn't stop, but our paper has to stop. So that's a cylinder. Now, I will say that the term cylinder sometimes in various books, and I think it might be true in our book, can say, look, what is a cylinder? It's something where we're missing a variable. And what that means is it says, if you're missing a variable, just plot it in the plane with the variables that you have, and then copy it. Okay, so here it is, our last example, our final thing. Sketch the surface z equals sine of y. Okay, so z equals sine of y. Now notice, this falls into cylinder because we're missing the variable x. So, how do we do it? Well, first off, just don't worry about the x for now. Just plot z equals sine of y. So I'm in the yz plane, thinking of y as my input, z as my output. So sine of y looks something like sine. Some people might say sinusoidal. Now, what do? Well, do you see this sine curve? It doesn't depend on which value of x I pick. When I'm in the yz plane, I'm picking x equals 0. So I can shift and say, look, I shift down, and now I'm going to draw the sine curve again. So I took the sine curve and I just shifted. Of course, I can shift this way, I can also shift that way, and I can again draw the sine curve. And computers are very good at drawing consistently, but you have to imagine that we could. And the point here is we're always just copying. So that what you see is something that's a rolling surface. And it's rolling along, no x dependence. So if I move in the x direction, it's always just a flat line. So it's like a goalie here. Flat goalie. So that's an example of a cylinder. All right, what are the takeaways from today? Well, the takeaways from today are, if you're not sure what's happening, look at the cross sections. Cross sections help build intuition and say, well, maybe if I understand what's happening in this particular cross section, I can gain insight. And that's how we often work with surfaces, is through cross sections. And then also keep in mind that some are going to be really important. In particular, look forward to the following. We're going to be talking about bowls and saddles later on in the course. So it's good to get a handle on what these things are now. And that's it for today. All right, to be continued next time.